Hey there guys, welcome to my channel. In this video I'm going to talk about the different types of probability distributions based on the different types of variables. So when we consider variables, there are two types of variables, right? It can be categorized into discrete random variables and continuous random variables. So when we consider discrete random variables are those who are definite. So they are definite and they take values which are specific. So considering you know having tossing a die, so you will be getting either 1 2 3 or any number between 1 and 6, right? So that is definite. So 1 and 6, so that is definite. It's not going to change anyway. So unlike continuous dynamics. So when we consider this, it's gonna be say for example we are considering the height or weight of in any country or in any state or in any town or city. So it might range between 150 to in centimeters. So the height might range between at maximum or 190 centimeter. So it actually can have any value between them, right? So it can be 150.1, 150.0025. So when we just consider the height, it can vary very much, right? Even minute variance might is considered as a different variable. So even 165.256, it's continuous, right? It actually has, there we can say there are like infinite values between them. So it's continuous between a range. So that is what continuous random variable mean. So let us also talk about the distribution that is followed by both of these variables. So when we consider a discrete random variable, then the type of distribution that is followed is probability mass function. So it's called as probability mass function. So whenever a discrete random variable or the probability of discrete random variable is plotted, it's called as the probability mass distribution or probability mass function. Also, when we consider the continuous random variable, whenever the probability of getting a continuous random variable is plotted, it's called as the probability density function. It's called as the probability density function. Okay, now let's look deep into the probability mass function and also the probability distribution function, how they are plotted. Probability mass function, probability distribution function. So consider we are throwing we are tossing a die. So the probability of getting one. So what's the probability of getting one? It's definitely six, right? So the sample space is 1 2 3 4 5 and 6. So either any of this is going to be coming for definite for sure, right? So probability of getting one will be 1/6, and probability of getting two will be 1/6. So it's all going to be same, right? So the probability of getting each of them, the problem. So 1/6 is actually 0.166 and so on, right? So this is gonna be like plotted here. So when we consider this, it's gonna be the probability of getting 1/1, and when while tossing, it's gonna be 1/6, right? It's gonna be 1/6, and even two is not gonna be 1/6, and we can say it's very uniform. It's very uniform, and this is the probability mass function for discrete random variables. So this is pretty much it. So this is the distribution when we consider any discrete outcome, right? Any discrete outcome. So let us consider the cumulative distribution function. So when we talk about variables, so let me just say discrete variables and continuous variables. Both of them will be like having different type of probability distribution functions. So as I said, this has probability mass function and continuous variable has probability density function, and both of them actually have a common type of distribution function, which is cumulative distribution function, which is very important. So both of them has cumulative distribution function for separate type of with having separate properties. So let us go back to the cumulative distribution function for discrete random variables. So this is the cumulative distribution function for discrete random variables. So when we throw dice, the probability of getting one, as I said, it's 0.166, right? So this was 0.16667, right? So the probability of getting 2 is here. When we consider the cumulative distribution function, the probability of getting 2 will be the sum of probability of getting 1 plus the sum of probability of getting 2. We know that probability of getting 1 is 0.1667, and also this is 0.1667. It's all same. So the sum of these two, the values, which is gonna be like ranging 0.3 something, which is less than 0.4. This is gonna be the value of probability when x is equal to 2. So when we see the cumulative word, the word cumulative itself, cumulative means summing up, right? It means summing up, right? For all, summing the all the range of possible outcomes that can be there. So it's just summing up. So when we see the probability of getting 3, likewise it's a probability of getting 1 plus 2 plus 3. So that is it. That is how probability of the cumulative probability works. So when we consider finally when we consider 6, the probability of getting 6, so we're going to be like summing up all of these probabilities. So this is how. So for 5 it's going to be till here. So the probability of getting 1, 2, 3, 4, 5, it's going to be a certain value that is plotted here. So when we plot each of them, the probability of 1 to 6, so it's going to assume a curve like this. So when we consider till 6, the 6 probability of course the probability of 6, it's going to be 1, right? When we say probability of 6, it's gonna be the sum of probability of 1 plus probability of 2 and so on till probability of 6, right? So of course it's gonna be 1 by 6 plus 1 by 6 plus 1 by 6 plus 1 by 6, so on, plus 1 by 6, it's gonna be 6 by 6, and of course it's gonna be 1, right? So by this we can just say that the when I is equal to 1 to 6, the probability of x is equal to I, it's gonna be 1. So we can say the cumulative probability always it's gonna be 1. So this is the case of discrete random variables, right? So when the sum when it comes to probability of getting 6 in discrete random variable, the cumulative probability, when I mean the probability of getting 6 is 1, I mean that it's the cumulative distribution function. The cumulative probability. When we consider this in terms of cumulative distribution function, the probability of getting 6 will be 1. So now let's move on to the continuous random variable. So this is another interesting type of variable. As I said, continuous random variable are present in the scenarios of when we consider height or weight, situations or any type of parameters wherein there are like infinite number of values, infinite number of possible values. So when we consider height, there are infinite number of possible height values. When we even consider 150 to 170 centimeters. So that can be like any infinite number of values. So we can't say there are like heights existing only this much. So it's not there. There's no certainty, right? So we have infinite number of values ranging between two specific values. So this is generally known as continuous random variable. So considering these are the examples of continuous random variables. So keeping this in mind, let us yeah, let us even consider the same. So this is the height that is distributed, and look at this beautiful bell shaped curve, right? So these are the heights that is plotted, and this is the probability. So when we see, when we let us just notice this curve. So at height 165, we notice that it's having a peak, right? So from this, we can say that most of the population's height is somewhere, around the 165. So the most of the population's height is like, so when we say 0.04, we mean that 4, or the 4% of the, so does it mean it's 4%? Yeah, it's actually the probability of the, it's actually the maximum number of chances of having the people in the height 165 in any specific region is maximum, right? So this is it. So when we talk about, say for example, we are having, it actually, this is actually known as the mean, right? When we say this is the mean. And yeah, we know in this is a normal distribution, right? So this is actually considered as the mean. 165 is the mean height, because almost, most of the heights are, having, the average height is considered as 165. Most of the people's height is lying around 165, less than or equal to 165, more around them. Yeah, so this is the probability density function. So when we consider the probability density function, the values ranges. So we can say there's no one who's, there are very few, there's no one, I mean, in the sense like, the people whose heights are, less than 165. So these are like equal to the people whose height is, more than 165, the percentage. So there's a 50 percentage of people who are, less than this, less than that. But most of the people, their heights, lie around 165 centimeters. So this is the probability density function, we can say. So when we consider the probability, the cumulative distribution function of continuous random variable, so here we have the same height. So when we consider this, we can say that when we see here, we notice zero point 0.5. What we mean by zero point 0.5 is, at the time when we are, traveling through the curve, when we reach 165, we mean that it's, 50% of the population is almost covered, 50% of the population. So just take a look at this. So when we see here, so here 50% means, this is 165, right? So this is half, halfway through it. We are like halfway through the population. So when we say it's like, uh, considering totally, we are like halfway into this, when we see it's like that. So when we consider, say for example, 158 something, so this will be like, say if it's like this, if it's 0.25. So we can say that we have passed through 25% of the population, and 25 percentage of the, people's height is being cumulated, or already it's being cumulated. So when we say it's just like cumulating, right? So when we cumulate till 165 centimeters height, we have already reached the middle state, or the 50% of the population. So when we consider 158, it means that we have like, say for example, 158 is around here. 158 is around here. So in this case, it'll be like around, lying around somewhere here. So in this case, we are like, when it's 158, we have like 0.02 percentage of the people are in zero having 158 centimeters height, and it's the 25% of the curve. It's actually the 25% of the curve, right? It makes sense, right? So that is how we go till 190 centimeters. So when we go till 190 centimeters, considering each of the height, we have cumulated totally uh, the entire curve, right? The entire curve. So when we cumulate the entire curve, we know that it's going to be one, right? When we cumulate, when we add up to all thing everything, so it's going to be one. So when we cumulate it totally, even for for the continuous variable, cumulative distribution function, of course, it's going to be one, because cumulation, in the sense, we are adding the probability of everything, one by one, and then of course, the sum of the probabilities of all the samples or every outcome, it's going to be one when we sum it. So that is it. It has the outcome as one. So that is it for this video, guys. Please do like the video if you found this helpful, and I'll be posting more videos on the probability mass function and probability density functions, and I'll be solving problems, and we'll get to derive the probability density function from the probability, from the cumulative distribution function. And I'll also talk about how to, whenever we here when we consider 165, we'll get to know how many actually lie in the height 165. So I mean, we can actually get to know the number of people lying in the range of 165 centimeter from this curve itself. So I'll be talking about each of them in the upcoming videos. Please do like and subscribe if you found this useful. Thank you so much, guys. Bye bye.